Hello everyone, welcome back, and in this section we are going to see about the evolution of word vectors and sentence vectors. We have learnt about TF-IDF, but at a broader context, let's even understand how TF-IDF represents words, sentences and paragraphs. This is going to be a very interesting comparison that you need to keep in mind. If anyone talks about any algorithm about word vectors or sentence vectors, think about how that algorithm will represent a single word, a single sentence, and a collection of sentences, which is a document or a paragraph. So let's understand how TF-IDF represents a word. So for example, if you just take the word Batman, you know that TF-IDF will calculate the TF-IDF value for the single word Batman. Essentially, a word is represented as a single value called the TF-IDF score. And remember that this TF-IDF value captures how frequent this word is in a given movie plot or document, and also how rare it is across all the documents or the corpus that we have. Although from any given document we can extract any word and calculate TF-IDF score, you need to remember that at some level you cannot really compare TF-IDF scores of different words and say that they are similar or dissimilar, because at the end of the day it's just capturing the corpus and document frequency and nothing to do with the relationships of different words with each other. So the thing to remember is that a word is represented by just a single value. And when it comes to sentence, let's take a sentence like Batman Begins is directed by Christopher Nolan. What happens is that again, this is going to be represented with a long vector, because we take the whole corpus and how many ever words that we have in the corpus, those are the columns or the features. So you can assume probably there are 60k features or 60k columns, and you realize that if you take Batman Begins directed Christopher Nolan, by ignoring the stoppers, you almost have just 5 non-zero values in this long 60k length vector. So a sentence is represented by a very long vector which is mostly sparse, that is, it contains mostly zeros, only few values are non-zero. And just extending that to paragraph, what happens is similar again. You basically have a very long vector of 60k length or so, and then probably you have 200 unique non-zero values, etc. if the paragraph has, let's say, 200 unique words. So at the end of the day, a word is just a single value. A sentence is a very long vector that is mostly sparse, and paragraph is also a very long vector that is also mostly sparse. Now the thing to remember is that TF-IDF can only help you on a high level when you want to do something like similarity matching or long document classification, etc. Then you can use this vector and compare against each other or do some classification tasks. So at the end of the day, TF-IDF metric essentially captures word frequency and word rarity across documents, and whatever comparisons that you do among different TF-IDF vectors, they are just matching similar words and frequencies with each other. And you can already see some of the shortcomings of TF-IDF, because you can only do like similarity comparison or classification on a very high level at document level, because you are essentially comparing word frequencies and word overlaps. And you need to remember that there is no word level similarity. That means a word like school is just as far from Batman as it is from college. Essentially, school and college should be closer together in high dimensional space, and Batman should be farther. But in TF-IDF case, school, Batman, college has just one single value, so you cannot really compare those values with each other. and TF-IDF values are very dependent on the corpus. And when you have short sentences, essentially you don't really have enough context to get good vector representations or doing comparisons with each other or classifications, because it's going to be a very sparse vector. And at the end of the day, all these shortcomings are significant in the sense that since you have very sparse vector, like for example, you have 100k columns and only very few values are filled, you cannot do any strong comparisons or classifications, etc. You can see that our immediate goal is to move away from just word frequencies, but rather capture word distributional semantics. That means which words co-occur with each other and what words come in the similar context, etc. Because we want to be able to compare school with college and say that these two are closer together when compared to Batman. And the other thing is that we need to move away from this sparse vector representation and come to dense vector representations. For example, if a sentence could be represented in just 364 length vector or 768 length vector, that's perfect for us, because now you can do comparisons of sentences or documents or paragraphs with each other, and also in a high quality manner, because these are dense vectors, they will also capture similar words together, etc. So exactly taking the point of TF-IDF where a word is not represented by a vector and you do not know anything about how similar two words are together, etc. To overcome that, we have this word vector algorithm. Essentially, word vector algorithm or Word2vec, as they primarily call it, what it does is to convert each word, for example, king, man, queen, woman, etc. Each of the word is converted into a long vector of length, let's say 368 or 768, etc. And the important thing to remember is that the word vectors are trained on a corpus in such a way that the vectors actually capture associations among different kinds of words. That means at the end of the day, if you have vector of king, vector of man and vector of woman, just like how you can do real world comparisons, if you can just add king vector with woman vector and subtract man, you will get another vector which is close to queen's vector. So at the end of the day, you can do quite a lot of comparisons, just like how real world mappings occur. You can do similar comparisons of word vectors. You can find the plural of a given word, or you can find the past tense of a given word, etc. And how are these word vectors trained? So just like you had movie corpus, you can take any large corpus, text corpus of data, for example from Wikipedia, and you can train your word vector algorithm on the whole corpus, and you can finally get the word embeddings. So what essentially happens is that you will take, let's say, single sentences, and within a sentence you will take some kind of sliding window. For example, for every given word you will take the left two words and right two words, and your goal is to predict the middle word when given the other keywords. So a neural network algorithm is trained to predict the focus word, that is the middle word or the prime word, given some surrounding words around the focus word. So let's make that clear. So for example, if you just have a sentence like Batman Begins is a 2005 superhero film directed by Christopher Nolan, what's going to happen is that you will take a sliding window of, let's say, 5 words. Here, if you come to this, then you have this 5-word sliding window where film is in the middle. So what's going to happen is that in the input, you again have all the unique words in the whole corpus. Then assume that there is a neural network. You don't really need to understand what this neural network does at the moment. All you can assume is that it's kind of like a black box. So given the surrounding words for this sentence, for example, 2005, superhero, directed and by, if you give those words as input to this neural network, it should be able to predict the missing word, which is film. So again, the output will have all the probable words in the corpus, maybe like 50,000 words or 100,000 words, etc. When I mean predict the word film, essentially each word in the corpus will be just associated with some token. So just you can think of it like a numbering scheme, and let's say this token represents, or this output represents the film word. All you are trying to do is adjust the weight of the neural network such that this output gets the highest score, which corresponds to the word film. So when I mean the input is words, again they are not simply words, they are just tokens or indexes. For example, 2005 could be some index and superhero could be some index, let's say 10th word or something like that. Just you give this whole corpus column here, and the output you have similar. So the neural network is trained such that you take this 5-word context, you give the input words, and you tune the neural network such that the output word is film. Essentially that particular output has the highest score among all the other. So there are several ways to train, where you can give the context words and try to predict the missing word or central word, or you can do the reverse as well. There are several ways to train word vector algorithms, but I'm just giving you a very simple example. So at the end of the day, what's going to happen is that you will take these 5-word contexts from the whole corpus. So if the corpus has, let's say, 100,000 movies or 10,000 movies, then you collect such sentences and you train the algorithm. For example, if you just give this context and ask a human to predict, what they'll do is they might predict movie or film, right? So similarly, when the word vector algorithm sees hundreds and thousands of these sentences, it will automatically identify that movie, film, cinema, all these words come closer together because the context, surrounding context is the same for all the words like film, movie, cinema, and it is going to generate vectors for film, movie, cinema such that those individual vectors are very close to each other. So at the end of the day, once this algorithm is trained, again food and related words are closer together, film and related words are closer together, or let's say you have Batman and related words, other superheroes, heroes like Spider-Man, etc. are closer together. And essentially what's going to happen is that for a given word, for example film, what we are going to do is, after the whole training is done on the whole corpus, maybe like 100,000 or 500,000 such 5-word context, if we take and train, we are going to collect the weight vectors of the last layer of the neural network that connects to film. So maybe there are 768 outputs at the very end that connect to film. And after the whole training is done, what we simply do is, for film, we collect the 768 length vector, and that's the word vector. Similarly, for food, there's a 768 weight vector that we collect, that's the word vector for it. And for the whole corpus, maybe like 50,000 or 100,000 words, for each of the word, we have a vector representation of length, let's say 768, etc. And the most interesting thing is that unlike TF-IDF, we have trained word vector algorithm by taking the distributional semantics or the surrounding words around a given focus word. So just because we have the surrounding context preserved, we are able to put together similar words in a closer vector space because of this training strategy. So that's the key that you need to remember. Now, coming back to our comparison of word versus sentence versus paragraph, what's going to happen is that any given word, for example, Batman, will have a single vector of 768 dimensions. So when I mean a single vector, it's just one long list of 768 numbers, and those values are just float values like this, 0.1234, 0.768 and all these things. And what happens with a sentence is that again we take a sentence and divide it by words. For example, here we have 1, 2, 3, 4, 5 words if we take out is and by as stop words. And what we are going to get is that we are going to get 5 vectors of 768 dimensions. And how do you get the sentence vector? Essentially, you just average the vector of individual words in this sentence and you get the final averaged vector that is of 768 dimensions. And same goes with paragraph. So paragraph, you take all the words, for example, maybe 100 words, and for each of the word you get the word vector and you average across all those 100 word vectors and you get the final paragraph vector or document vector. So at the end of the day, remember that for TF-IDF, there was no vector, there was just one single value. And for sentence in TF-IDF, there was a sparse vector of very long length, and similarly for paragraph. But when it comes to Word2vec, unlike TF-IDF, instead of a single value, we have a single vector that is of 768 dimensions or whatever dimensions you trained for. And in sentence, you have dense vector instead of a sparse vector. So instead of 50,000 dimensions, etc., you have a dense vector that is of 768 dimensions or 360 dimensions, etc. And similarly for paragraph, you have a dense vector as well, which is of fixed dimensions. Now the interesting thing to remember is that still with word vectors, we have some issues. TF-IDF had some issues. We tried to solve some of them and we made a better representation with Word2vec. But still Word2vec also has some shortcomings that we need to overcome. So the first thing is there is no word sense disambiguation. What I mean by that is if you take a word like mouse, that could mean a computer mouse or it could mean the house animal mouse. The thing is that there's only one entry in the lookup table of Word2vec. So it does not hold two different embeddings for these two different senses or contextual meanings. So at the end of the day, if your corpus has both computer mouse and the house mouse, then the word vector for the mouse will be confused and it's kind of like an average between these two contexts. So it will not really capture the context correctly. So the short thing to remember is that since there is no word sense disambiguation, for words that have multiple meanings, still we are going to have just one single vector, and that might not be ideal for most of the use cases because we need to have vectors that are contextual for a given word. And the other thing to remember is that if you are trying to get sentence vector, what we are trying to do is we are just averaging the word vectors of individual words in the sentence to get a sentence vector. But that doesn't really suffice because sometimes you need smart weighted averaging because some words are more prominent or important than the other words. So you need to give weightage to the sentence vector such that those words and their corresponding word vectors have a higher score, higher weight factor when you're averaging, but that's not preserved when you're trying to take sentence vector. And the other thing to remember is that if you just take plain Word2vec algorithm, if a certain keyword is not there in the dictionary lookup, that is the vocabulary created after Word2vec algorithm, then that word is completely ignored. What I mean by that is, let's say if you have a sentence like Ramsri is going to college, then going college will have word vectors in the vocabulary of Word2vec, but Ramsri, the word will not be present. So when we take the average sentence vector, we are going to completely ignore Ramsri because it is considered as out of vocabulary word. After Word2vec came out, which is one of the first algorithm to do this word to vector conversion using neural networks, there are several variants that came out, and one of the variant was called as fast text by Facebook. And fast text, what it does is that a given word, if there is no direct entry available in the vocabulary to get the word vector, it is going to split that word into sub words. So essentially a word like Ramsri could be divided into RAM and Sri, which might individually have entries in the word vector algorithm. So our sentence Ramsri is going to college will now be Ram and Sri combined with going to college and averaged out. Essentially at the end of the day, if you have a sentence like Ramsri is going to college, whichever word, in this case Ramsri, doesn't have a direct entry in the vocabulary of Word2vec algorithm or word vector algorithm, fast text will split the out of vocabulary word into its subword tokens, where each of the token will have entry in the fast text vocabulary, and we'll just take sum or averaging of that when we are considering the sentence vector of the whole sentence. So at the end of the day, you need to understand how the word and sentence vectors have evolved over time, how the algorithms have evolved, etc. And all you need to have most of the time is to have a strong understanding of the pros and cons of each of the word or sentence vector algorithm and use them accordingly. And on any day when you need to know more, you can go and delve deeper into a particular algorithm to make any changes, etc. But from a practical applied NLP standpoint, if you just have a good baseline understanding of TF-IDF, Word2vec, and all the variants up to sentence transformers, that's good enough. So let's just see how word or sentence vectors have evolved over time. So in the first category, we have TF-IDF, which falls into the category of sparse embedding. And we know that Word2vec attempted to solve this sparse embedding problem by providing a dense embedding because of its training strategy that involved training a neural network algorithm with corresponding surrounding words around a given word. With that, we were able to put together similar words in a closer embedding space. So the vectors for similar words are close together. And because of the power of dense embedding as well as vectors being close together, whatever real world operations that we can think of, we are able to kind of emulate them in the word vector space as well, which is king minus man plus woman is equal to queen, as well as any noun comparisons. For example, plural of mouse is mice. Similarly, elephant is elephants, etc. So you can do comparisons like mice minus mouse plus elephant is equal to elephants, etc. And we have seen the problem with Word2vec, which is it cannot differentiate between different senses of a word. For example, between computer mouse and the house mouse. And also we have seen that when it comes to sentence embedding, we are just averaging out the individual word vectors. So there is no weightage or importance given to certain keywords, etc. And the next evolution from Word2vec is actually sense2vec. So during training, what we can do is we can append each word with its corresponding POS, parts of speech, or NER, named entity recognition tag. What I mean by that is, let's say you have a word like bank. Bank could be a verb. Bank could be a noun, financial bank, whereas verb could be like depend on somebody, banking on somebody, etc. So in such cases, all you can do is, in the context where bank is verb, you can replace bank by bank_v, and in the context where bank is noun, you can replace bank underscore n, and you can train a word vector algorithm, parts of speech appended entities, so that when during query time, when you give bank underscore n, instead of getting depend and other things as the near word vectors, you will mostly get financial bank related word vectors like loan, etc. That's what you can do. So sense2vec is actually an improvement over Word2vec, where you can actually append the sense of a given word even. And also you have seen that to counter out of vocabulary words, we have fast text, which can divide a given word into its subtokens. Again, sense2vec is limited because when you take the case of mouse, mouse is a noun in both computer mouse as well as the house mouse. So you cannot really differentiate with the parts of speech tag. The other thing that you can do is give a named entity recognition NER tag as well appended to it. But like I mentioned, still it has some shortcomings. So over TF-IDF we have Word2vec, and over Word2vec we have sense2vec, but still we do have some issues which are, one, we are unable to fully resolve the context of a given word, so we are unable to do word sense disambiguation, so we still need contextual embeddings. Secondly, we don't really have word importance captured because we are still doing lookup for a given word and getting its word embedding. And when you are getting sentence vector, you are just plainly averaging the word vectors, whereas we want to also calculate the importance of a given word, so we want to change the weights, or we want a single word to have more context and its embedding should come from context across the words that are surrounding it. And ELMO and BERT fall into this category of contextual embeddings. So essentially, if you give a sentence, for example, I am going to the bank to deposit some money, in that case automatically the word bank will have a different word embedding when compared to another sense where I am going to the river bank. In both the sentences, bank is a noun, but since the context is different, you'll have contextual embeddings because of algorithms like ELMO and BERT, etc. For simplicity, you can think of ELMO as the first contextual embedding that came out, which tried to solve this word sense disambiguation problem that you had with mouse, bank, etc. And then came algorithms that specifically focused on sentence to vec approaches. We just realized with Word2vec that although we are able to get the perfect embedding for a given word, just averaging the word vectors of words in a given sentence and getting a sentence vector doesn't really suffice, because plain averaging doesn't capture the complete picture of a sentence, whereas we should be able to do some smart averaging across the word vectors of individual words in a sentence. So in order to solve that, several algorithms like skip thought vectors, infercent, and universal sentence encoder came into existence, which is instead of dealing on a word level, they directly deal on a sentence level to give a unique vector for the whole sentence such that similar sentences are closer together. And these algorithms, skip thought vectors, infercent, universal sentence encoder, most of them used RNN, recurrent neural networks like LSTMs and GRUs, in order to generate these sentence embeddings. Of course, universal sentence encoder had a variation which used transformers, which is the advanced algorithms that captures relationships among different words in order to get an embedding for a given word. And moving further on, current state of the art is actually sentence transformers. So these are transformer based algorithms that are trained on top of BERT, etc. to encode sentences specifically to keep similar sentences closer together in the vector space and dissimilar sentences farther together in the vector space. So they are fine-tuned on top of BERT-like algorithms to produce high-quality sentence embeddings. And one thing to remember is that not only words or sentences or paragraphs are converted into vector, even images could be converted into vectors. So there are models like CLIP and several vision algorithms that can convert a given image into a single vector of fixed dimensions so that you can compare images among each other, etc. So if you come to sentence vector improves on top of the word vector. So you can see that the biggest shortcoming of Word2vec was there was no word sense disambiguation. Secondly, the average vector was pretty simple, just averaging across all the words. So sentence vector essentially solves that problem, where although it is termed as sentence vector, you can just give an individual word or just a phrase even and get vector out of it. For example, you can just give a single word like Batman and get a vector, or you can give multi-word like Donald Trump or Joe Biden, etc. and also get a vector, or you can give a sentence and a whole paragraph and get a vector. So at the end of the day, again, just like Word2vec, sentence vectors, that is sentence transformers, can convert a single word or just a phrase into a vector directly of 768 dimensions. And again, a sentence could be converted into a single vector of 768 dimensions. The only difference is that in word vector algorithms, we just averaged out all the individual word vectors in a given sentence. Whereas when it comes to sentence vectors, what happens is that, for example, a given word like directed does not independently have a vector of its own. Rather, the directed vector comes from a combination of all the surrounding words to the left and right of this. So you can kind of imagine that whatever we wanted to do, which is smart weighted averaging of word vectors in Word2vec algorithm, we kind of do that in sentence transformer inherently, where each individual vector that we get is actually a smart weighted combination of other vectors. And at the end, we also combine, average out all the vectors that we have in order to get the single smart vector. But remember that in Word2vec, we have kind of a lookup table scenario where individual word and its vector is obtained. Whereas in this case, this individual vector is not pre-calculated and kept in a lookup table, but rather generated dynamically depending on the sentence. So that vector is very efficient and it captures all these complexities like word sense disambiguation, like mouse in both cases, as well as the relationship of that word with respect to the corresponding words that are to the left and right. So you can assume that unlike word vectors, this is a smart vector that is of 768 dimensions. Similarly, for paragraph also it's the same. We essentially have a max length, usually 1024 tokens or tokens converted to some word count like 512, etc. So sentence vectors, etc. can take, let's say, a paragraph of maximum 500 words, etc. and it can generate a smart vector even. So at the end of the day, a word is represented by a single vector. A noun phrase or verb phrase that is multi-word is also represented by a single vector. A sentence is represented by a single vector. A whole paragraph or document is also represented by a single vector. So now you can do easy comparisons among each other. So just to recap everything that we have learned, we have TF-IDF for high-level document comparisons and classifications as well, but it has quite a few shortcomings. One is there is no word similarity that is embedded. Second is the vectors are very sparse. Most of them are zeros. So we moved from that to dense vectors. That is, instead of having 50,000 length, we have now 360 dimensions or 768 dimensions length vector. So Word2vec was one such algorithm. In order to tackle subwords, we have fast text, and in order to have word sense disambiguation, we introduced sense2vec. And beyond that, we have ELMO, which actually gives contextual embeddings and performs better than sense2vec. So I just kept all of these algorithms from Word2vec to ELMO in these dense word vectors, because each of them improves over the other by solving some of the shortcomings of the before one. Now we realize that just getting vectors for word isn't sufficient. We need to do better, that is smart averaging, to get a sentence vector, because a sentence vector is not just plain averaging of individual word vector. We need to have some kind of weight or importance factor also captured in the sentence vector when we are getting the combined thing. So these algorithms like skip thought vectors, infercent, universal sentence encoder, USE, improved on word vectors and tried to get us sentence vectors or document vectors straight away that are of higher quality that we can use for comparisons. But still they had some shortcomings, in the sense that the vectors are not of high quality. And then came sentence transformers, which is based on transformer based algorithms for sentence vectors. Although it is called a sentence vector, it can take a single word or a multi-word phrase or a sentence or a document and generate vector, single vector of, let's say, 768 dimensions. And this is currently the state of the art, the sentence transformers and its variants, and they are the ones that are used in cutting edge state of the art projects, NLP projects. So the practical guide is that if you are doing lightweight classification or high level comparisons, you can use TF-IDF vectors if you have a lot of corpus. If you don't have the corpus and you want to do again lightweight classification and comparisons with dense vectors, you can go for Word2vec, because you don't need to have any corpus or pre-train anything. So averaged word vector and doing classifications or comparisons is a good baseline. But if you really want to hit it out and get state-of-the-art accuracies, you can use sentence transformers. And the power with dense embeddings is that even if you have 1 million or 10 million documents, you can just convert each of the document into a single vector using sentence transformers, and you can place all those 1 million or 10 million documents in a vector database that is specifically designed for comparing vectors among each other. Now let's say you have a new movie plot or new document, you can convert that into a vector and do very fast comparisons across all the 1 million or 10 million documents that you have, comparing the vectors to fetch the most similar vectors, etc. So essentially, remember this thing. If you don't want to do heavy computation and want to do something very quickly, you can use pre-trained Word2vec algorithm and just get your embeddings and average embeddings and do comparisons. That's rule number 1 to remember. Rule number 2, if you want to get state-of-the-art accuracies, go for sentence transformers. Thanks for watching.